By now, the concept of nearly everything being digitized is commonplace. Radio signals, photographs, audio, video, nearly everything can be digitized. That's clear. But what isn't clear to many of us is how does a computer handle numbers at all? Well, I'm glad you asked. We humans developed a base 10 number system since we first learned to count on our fingers. We have 10 fingers, so we have 10 different digits, 0 through 9, to represent that. As we count up to the 10th finger, we reset the count to 0 and carry a digit to the next higher number. So the digits represent, from right to left, ones, tens, hundreds, thousands, and so on. That's 10 to the 0th power, 10 to the 1st power, 10 to the 2nd, and beyond. So 8,364 is actually 8 times 1,000, or 10 to the 3rd power, plus 3 times 100, or 10 to the 2nd power, plus 6 times 10, or 10 to the 1st power, plus 4 times 1, or 10 to the 0th. That's how we all have numbered things since the 1st grade. But what about an intelligent alien species that only has one finger on one hand? How would they count and keep track of numbers? Well, consider a light bulb that has only 2 possibilities, on or off, a switch that has only 2 positions, up or down, or a transistor with only 2 states, conducting or not conducting. The latter is exactly what is happening in a digital electronic system. Each element in the circuit is either energized, represented by a 1, or it is not energized and represented by a 0. It is the same as an alien with only one finger who thinks mathematically in a base 2 numbering system, a binary system. Okay, so how does that work? The right-hand bit, or least significant bit, is worth 2 to the 0th power. The next is worth 2 to the 1st power, then 2 to the 2nd, and so on. 2 to the 0th power in decimal is 1. 2 to the 1st power in decimal is 2. 2 to the 2nd power is decimal 4. 2 to the 3rd is 8, then 16, 32, 64, and finally 2 to the 7th is decimal 128. Note that each position is worth twice the value as the digit to the right, or half the value as the digit to the left. Since we have only 2 digits, each position can only be a 1 or 0. In an electronic device, that is represented by a 1 for a voltage higher than some certain amount, or being 0 if it is not. So how do we count in a base 2 system? Let's start. Adding a 1 to the least significant bit is 0 plus 1, or 1. Add 1 to that, and we get 1 plus 1, which is 0 with a carry to the position to the left, just like decimal counting. Add 1 again, and it's 0 plus 1, or 1. Add 1 to that, and it's 1 plus 1, which is 0 with a carry. Now the second position is 1 plus 1, which is 0 with a carry to the position on its left, and so on and so on. Let's watch it count for a few cycles. Now, how do we relate this long binary string into a decimal format that's easier for us 10-fingered humans to relate to? Let's start with the binary number 10110110. Since we know the value of each position, it's a simple matter of adding them up. 1 times 128 plus 0 times 64 plus 1 times 32 plus 1 times 16 plus 0 times 8 plus 1 times 4 plus 1 times 2, plus 0 times 1, or decimal 182. With an 8-bit number, we can represent any decimal number from 0 to 255. If we need to represent a number higher than that, simply add 8 more binary digits to the left to represent 256, 512, 1024, 2048, 4096, 8192, 16,384, 32,768. With a 16-bit binary number, we can represent any decimal number from 0 to 65,535. Classic definitions call a single-digit binary number a bit. 4 bits are a nibble, 8 bits are a byte, and 16 bits are a word. So now you know how an IC memory element with individual wires representing on or off, yes or no, 1 or 0, can represent decimal values. So what can we do with binary numbers that can be recognized by digital circuits? Gosh, sky's the limit.